South Atlantic Anomaly, have astronomers finally explained space's Bermuda Triangle. Ships, airplanes and people have been known to disappear without explanation in an area of the North Atlantic Ocean known as the Bermuda Triangle. Could it be extraterrestrials, some force pulling objects under the sea, or linked to the fabled lost city of Atlantis? Or could it simply be bad weather, human error or heavy traffic in the region? No one knows for certain, but more than 50 ships and 20 planes have vanished since the mid-19th century. That's actually no more than in any other well-traveled area of the ocean, but still, the conspiracy theories persist. If we look skyward, we can explore a similar phenomenon dubbed the Bermuda Triangle of space. This vast region above Earth has been known to wreak havoc on spacecraft that happen to enter the area. The craft aren't suddenly vanishing into thin air, but the disruption that's caused is nevertheless serious, and it poses problems for both equipment and astronauts. The Bermuda Triangle of space lies above the South Atlantic, stretching from Chile to Zimbabwe, and sits at the point where the inner Van Allen radiation belt comes closest to Earth's surface. Earth has two Van Allen belts, which are two donut-shaped rings of charged particles that surround our planet, held in place by Earth's magnetic field. The inner part consists mainly of high-energy protons and the outer part is mainly electrons. Because the belts trap the particles that are shooting from the surface of the sun, they end up protecting the surface of the planet from harmful radiation. At the location of the Bermuda Triangle of space, or the South Atlantic Anomaly SAA as it is formally known, Earth's magnetic field is particularly weak. This means the particles of solar cosmic rays are not being held back to the same extent as they are elsewhere above the planet. As a result, solar rays come as close as 200 kilometers (124 miles) to the Earth's surface. The more intense solar radiation results in an increased flux of energetic particles in this area. I'm not fond of the nickname, but in that region, the lower geomagnetic field intensity eventually results in a greater vulnerability of satellites to energetic particles, to the point that spacecraft damage could occur as they traverse the area, said John Tarduno, professor of geophysics at the University of Rochester. The lower magnetic field intensity allows Earth's radiation belt, technically the inner belt, to come closer to Earth's surface, Tarduno told All About Space. Thus, satellites passing through this region will experience higher amounts of radiation to the point that damage could occur. Think about an electrical discharge or arc. With more incoming radiation, a satellite can become charged, and attendant arcs can result in serious damage. The Bermuda Triangle is one of the most dreaded areas on the planet due to terrifying stories of ill-fated ships and planes that have ventured into it, some 1.3 million to 3.9 million square kilometers, 500,000 to 1.5 million square miles, and disappeared without a trace. These disappearances are often blamed on paranormal forces, such as aliens, sea monsters, and mythical cities that lie within its waters, but scientists argue that natural forces and human error are more likely the cause. What happens to spacecraft and astronauts in the SAA? Ordinarily, the Van Allen belts stretch at an altitude of between 1,000 and 60,000 kilometers, 620 and 37,000 miles, above Earth's surface. The low altitude of the radiation hotspot, however, puts it within the orbit of certain satellites, which become bombarded by protons that exceed energies of 10 million electron volts at a rate of 3,000 hits per square centimeter per second. This affects the spacecraft's onboard electronic systems, which hampers the operation of these objects and forces space agencies and other satellite operators to power them down. The same goes for the Hubble telescope, which passes through the SAA 10 times a day, spending a good 15% of its time there. Hubble is unable to collect astronomical data during these moments, which is not ideal, but necessary. All About Space magazine takes you on an awe-inspiring journey through our solar system and beyond, from the amazing technology and spacecraft that enables humanity to venture into orbit, to the complexities of space science. Failing to take precautions by shutting the spacecraft down would likely lead to system failure, something astronauts have already witnessed with computers on board craft that fly in the vicinity of the SAA. The only solution is to take protective measures. Putting equipment into a safe mode means operations that are more vulnerable to radiation are curtailed, Tarduno said. The more complex electronics have become, the more potential there is for problems to emerge. Any satellites that use the microwave tracking system DORIS, which stands for Doppler orbitography and radio positioning integrated by satellite, for example, see a resulting shift of the onboard oscillator frequency. Damage caused by the SAA can also prove very costly, as evidenced when the area sent the Japanese satellite Hitomi crashing down to Earth. Hitomi, or Astro-H, was commissioned by the Japan Aerospace Exploration Agency JAXA to study extremely energetic processes in the universe. Just over a month after its February 2016 launch, its operators lost contact and the satellite broke into several pieces. Experts later discovered that the problem was due to the spacecraft's inertial reference unit, a type of motion sensor, reporting a rotation of 21.7 degrees per hour when the craft was actually stable. When the attitude control system sought to counteract the non-existent spin, a succession of events caused it to break. Had the operators been able to spot the error in real time, they could have corrected it. But it happened while the satellite was traveling through the SAA, so communication was lost. There is also a possibility that the large dose of radiation affected the electronics. In any case, the unfortunate saga cost JAXA about $273 million and 3 years of prepared studies. Astronauts can be affected by the SAA too. Some have reported seeing odd white lights flashing before their eyes, and steps have been taken to protect astronauts on board the International Space Station ISS. Strong shielding is in place over the most frequently occupied parts of the ISS, such as the gallery and the sleeping quarters, to reduce the amount of radiation the astronauts are exposed to. Astronauts also wear dosimeters, which are devices that measure their personal exposure to ionizing radiation in real time, and send out a warning if they reach dangerous levels. How the South Atlantic Anomaly SAA is created. What causes the SAA? But why is the magnetic field less strong above the South Atlantic? It's because of the shape of Earth, which is not completely round. The Earth bulges slightly in the middle, and the planet's magnetic dipole field is offset from its center by about 500 kilometers (300 miles). Where the deep lies, the charged particles and cosmic rays are closer to Earth's surface and provide less insulation from interplanetary space. Even so, this magnetic bubble still prevents solar wind from reaching the surface. The magnetic field is sustained by a dynamo process that results from the flowing liquid metal in Earth's outer core that generates electric currents. When the planet rotates on its axis, the turbulent movement of molten, charged material is what forms the magnetic field, and gives the planet the north and south poles at the surface. Yet the poles aren't permanent, as Earth's magnetic field is constantly shifting, growing stronger and weaker as it moves around. At the moment, the magnetic field is weakening in the area of the SA, which means the area growing. Tarduno and his colleagues have been studying how long the SA has been active. In 2018, they found a unique source of geological evidence in Africa that helped shed light on what Earth's magnetic field looked like thousands of years ago. Bantu farmers who lived in the Limpopo River Valley in Africa 1,000 years ago would perform a cleansing ritual which involved burning their villages during droughts to start afresh and encourage the rain. The burn resulted in the freeing of magnetic minerals in the clay that would align with Earth's magnetic field before cooling, which left Tarduno and his colleagues a stunning snapshot of what the magnetic field looked like at that time. We found something unusual about the core mantle boundary under Africa, Tarduno said, which could be affecting the global magnetic field. The team found evidence that the SA is the most current manifestation of a recurring phenomenon. Under Africa, at the core mantle boundary just above the liquid iron core, the field is reversed. This is something we call a reversed flux patch, Tarduno said. It is this patch that seems to be causing most of the weak field in the SA. Scientists have also looked into whether this will mean the magnetic field is about to flip, but studies based on observations of the past 50,000 years suggest the SA is not a sign of this. A close-up of a logo, an artist's impression of the proton-dominated inner belt red, and the outer belt, which is made up of electrons, blue. Provided by space, an artist's impression of the proton-dominated inner belt red, and the outer belt, which is made up of electrons, blue. What the SA expansion means for Earthlings and space travel. Further studies have also looked into how hazardous the radiation in the SA could be at different levels. This is important because the growing area of the SA will not only increase problems with computers and other electronic equipment on Earth, but it could also lead to a greater prevalence of cancer. Riccardo Campana at the National Institute for Astrophysics in Bologna, Italy, analyzed radiation data from the Italian-Dutch satellite for X-ray astronomy BeppoSAX, which frequently journeyed through the lower edge of the SA between 1996 and 2003. He found that radiation levels were lower in the lower part of the SA than in the upper layers. Still, as the European Space Agency points out, the magnetic field in this area has lost about 15% of its strength over the past 150 years. Before 1994, the magnetic North Pole was moving at 10 kilometers, 6.2 miles per year, but this has sped up to some 65 kilometers, 40 miles per year since 2001. Could the magnetic field ever disappear completely, leaving Earth wide open to radiation? This is not a concern until many billions of years into the future, Tarduno said. Even during times of magnetic reversals, there is a magnetic field, albeit much weaker and much more complex in form than the present one. The debate now is whether we are in the early stages of a magnetic reversal. The rapid decline in dipole magnetic field strength over the last 160 years and the pattern of decay lend some support for consideration of this as a possibility, but the short time span of the observed decay still puts this into the realm of speculation. For now, the main concern is for space exploration, particularly given that the number of satellites and spacecraft carrying humans is set to increase. Knowing how the SAA behaves is crucial because as it grows at a rate of 19.3 kilometers 12 miles per year, it will soon end up covering a much greater geographical region than it does today. Don't forget to like and subscribe to our channel. We will upload more interesting news and information on coming days. Thank you for your visit.